This is Math 151, and we're going to begin Unit 3 now. We're done learning all of those different rules for derivatives. You've got all the rules you're going to get, in this class at least. And we're going to turn entirely to looking at applications of the derivative. Now we've done some, right? We know that the derivative is the slope of a tangent line. We know the derivative is the velocity of a position function. And we also know that the derivative is, in general, an instantaneous rate of change. We'll be relying on several of those ideas as we look at the applications in Unit 3. Our first topic, Topic A, is related rates. The concept behind related rates is that when things change, they usually don't change in isolation. Usually things change together. Here's a simple example. A spherical snowball is melting. The radius decreases by 2 centimeters per hour. How fast is the volume changing when the radius is 10 centimeters? So the change in radius causes a change in volume. How fast the radius changes affects how fast the volume changes. Two rates that are related to one another. So that's why the whole concept is called related rates. So I'm going to go ahead and I'm going to begin almost all of these problems by drawing a diagram and then filling in this little chart that, at least for me, I think it really helps organize the information in a problem. So this is just a spherical snowball. And it's got some radius, r. All right, reading the problem, it says the radius decreases by 2 centimeters per hour. That's a known rate of change. So the radius decreases by 2 centimeters per hour. It's my known rate. The rate of change of radius, I could write as the derivative of the radius. And notice this is changing over time. So this derivative would be with respect to t, the time variable. And it's decreasing, so that would be negative 2 centimeters per hour. All right, next, we're asked, how fast is the volume of the snowball changing? That's our unknown rate. We would like to know the rate of change of volume, but we don't know it yet. So that's my unknown rate. It's volume, so I'm going to call it the rate of change of volume, dv dt. How fast always refers to time, and in fact I might as well just say right now that in related rates, time is always going to be your independent variable. And I don't know the answer to that yet, so that's my unknown. Finally, I want to know this specifically when the radius is 10 centimeters. So I'm going to put when, and in terms of my variables, my radius, I called it r. So when r equals 10 centimeters. All right, if you've organized your information in this little chart, the next step will always be to write an equation, and you need to have the equation show a relationship between the dependent variables from your derivatives. So in this case, my dependent variables are the r and the v. So I need to write an equation relating r and v. In this case, it's going to be the volume of the sphere. And by the way, if your geometry formulas aren't super fresh in your memory, I'll just call your attention to the fact that you do have a list of geometry formulas in your formulas list. And for a sphere, the volume is 4/3 pi r cubed. So once you've got your equation, and notice it does give me a relationship between v and r, my next step is to take, and it's going to be an implicit derivative, all derivatives here are with respect to time, so with respect to t. So the derivative of this will be dv dt, and that's going to equal 4/3 pi, constant multiplier, times the derivative of r cubed, which would be 3r squared, and here's the implicit part, right? Chain rule would give me a times dr dt there. All derivatives are implicit in related rates problems. All right, I'm going to clean that up a little bit, but all I can do there is reduce that, get rid of those 3's, and I'll have 4 pi r squared dr dt. The last step is to substitute in the values from the little table that we made. So, going back up to the table here, I can put in -2 for dr dt and 10 for r. So I'll have 4 pi times 10 squared times -2, which allows me now to solve for exactly what I wanted to know. The rate of change of volume, dv dt, is going to be a -800 pi. And let's see here. These were units of centimeters and hours, so a volume would be in cubic centimeters per hour. And that has solved my problem. Now notice, that's an instantaneous rate of change. That's right at the moment that the snowball has a radius of 10 centimeters. If the snowball was bigger or smaller, I would have a different instantaneous rate of change. So these are always rates of change at a particular moment in time when something's happening. These same 3 steps that I've outlined here, write an equation, take an implicit derivative, and sub in the values, going to be the same 3 steps that I'm going to use in every single one of these problems. I won't necessarily write out the words every time, but you can go back to see those 3 steps that we'll always use. All right, we'll do several examples of related rates problems. Just one of those things, the more of them you see, the easier they get. So we'll do a number of them. In our second example, a conical tank, point down, is being filled with water. The tank has a radius of 10 feet and a height of 12 feet, and water is pumped in at the rate of 5 cubic feet per minute. How fast is the water level in the tank rising when the tank is filled to a height of 8 feet? Again, always a picture. Helps me organize things a lot. So here's my tank in the shape of a cone, point down. I do know, oops, sorry about that. I do know that the radius of this tank is 10. So up here at the top is 10. And the height of the whole tank is 12. All right, the tank's not full yet though, right? Water's getting pumped in at a particular rate. And so I'm going to show my water level in the tank. Down here, my tank's only filled up that far. What that does is it makes sort of a mini cone. And that little mini cone is going to have its own radius and its own height. So there's the radius for the little cone, r, because that will change as the water fills up, and h for the height of the little mini cone. All right, let's go back to the problem and take a look at our known and unknown rates. We were told that water is pumped in at the rate of 5 cubic feet per minute. That's my known rate. That's a change in volume, right? Cubic feet. So the derivative of the volume with respect to time, and water's going in, so it would be positive 5 cubic feet per minute. The question that we're asked is, how fast is the water rising? So let's see, the water level in the tank, that would be the height. So we would like to know dH dt, but it's unknown right now, so dH dt is what I'm trying to find. And I want to do this specifically at the moment when the tank is filled to a height of 8 feet. So when h equals 8 feet. All right, information's all organized. The next thing I need is an equation that relates v and h, my two dependent variables. Now it seems like the obvious equation to write here would be the volume of a cone. And I can certainly do that. Volume of a cone is 1/3 pi r squared h. But I have a problem here, and this is a problem that's not uncommon in these kinds of problems. I actually have too many variables, right? I wanted a relationship between r and h, but I have this extra variable r in here, and I can't take the derivative until I'm down to just one variable on the right-hand side. So in order to do that, I'm going to go back to my picture, and I'm going to say, is there any way that I could come up with some kind of an extra equation that I could use to get rid of my extra variable? What I'll do here is I'll use similar triangles. This large triangle and this small triangle are similar, so I could write the statement of proportionality that, let's see, what would it be? 12/10 is equal to h/r. If I used my cross multiplying, I would have 12r equals 10h. And I'd like to solve for r because I want to substitute for r. So r would be 10h divided by 12, or 5/6 h. Okay. So let's go ahead and plug that in. I'm going to replace the r with 5/6 h, and that gets squared, times that h. And now notice my volume, v, depends only on the variable h. There's no more r's, and I'm in good shape. Now I would like to do a little bit more algebra before I take the derivative, because it will make my derivative easier. I'd have 1/3 pi times 25/36 h squared times h, or 25 pi h cubed. Actually, let me do all the numbers first. 25 pi on top, 3 times 36 would be 108 on the bottom, and then h squared times h would give me h cubed. There. That's a lot easier to take the derivative of. So now I'm ready for my implicit derivative with respect to time. dv dt equals this constant multiplier, 25 pi over 108, times the derivative of h cubed, 3h squared, dh dt. Right? Again, keep in mind, every single derivative you do, both sides of the equation, it's always going to be implicit. All right, tiny bit of algebra here. There's not a whole lot I have to do. I could reduce the 3 and the 108, I guess, and make it a 36. So I have 25 pi over 36. Oops. 25 pi over 36. H squared dh dt. I've got my derivative. Now I can start plugging in my numbers. If you look back up at the chart we made at the top of the page, dv dt was 5. That's equal to 25 pi over 36. And we wanted to plug in an 8 for h times the dh dt, that's our unknown. So, let's see, I know 25 times 64 is 1600 pi over 36. So I'll have 5 times 36 over 1600 pi. Which is approximately 0.0358. That's a rate of change of height, and in the units that we're using here, that would be in feet per minute. All right, let's see, let's do one more on this video, and then we will start a new one. In problem 3, our boat's being pulled in by a rope attached to a pulley at the edge of a dock. The dock is 12 feet above the surface of the water. The rope's pulled in at the constant rate of 3 feet per second. How fast is the boat approaching the dock when there are 30 feet of rope out? So once again, picture's worth 1,000 words, right? Let's do it. Let's see here. If this is my dock, and this is the water, here's my boat. I know that the dock is 12 feet above the surface of the water, so this is going to be 12 all the time. The rope itself goes from the pulley at the edge of the dock to the boat, and the length of that rope is going to change. So I'm just going to call it R for the rope. How fast is the boat approaching the dock? That would be this distance here. Let's just call that X. Okay. By the way, when I draw my picture, notice that I'm really careful. I only label things with numbers if they don't change, right? Things that are going to change, like the length of the rope, the distance from the dock, I always use variables for those. And now when I go up to start filling in my chart, I'm going to be sure that I use the same letters, the same variables as I used in my diagram. Otherwise, the problem gets really confusing. All right, known rate. The rope is pulled in at a constant rate of 3 feet per second. So that's going to be the change in R from my picture, dr dt. Keep trying to dismiss that. What's going on? There we go. That's going to equal, let's see, the rope's getting pulled in, so R is getting shorter. That will be a -3 feet per second. All right, the unknown rate. We want to know how fast the boat's approaching the dock. That's the rate of change of this distance that we've called x. So dx dt is what I'm trying to figure out. And specifically, I'd like to do this when there are 30 feet of rope out. So when R equals 30. All right, so I need an equation that gives me a relationship between these dependent variables, R and X. And if I look at this, I've got a nice right triangle here. So I'm thinking in this case, the Pythagorean theorem would be a great way to go. X squared plus 12 squared equals R squared. Or X squared plus 144 equals R squared. This is perfect. The only variables are R and X. It's exactly what I wanted, so I don't need to make any adjustments. Let's go ahead and take our implicit derivatives. We'd have 2x times dx dt plus the derivative of 144 is just 0 equals 2r times dr dt, implicit derivatives again. Of course, the plus 0 doesn't do anything, and I could divide the 2's out of both sides. So I'd have x dx dt equals r dr dt. All right, I would like to substitute in my values. And before I do that, I want to point out kind of the sticky point in this particular problem. It's okay that I don't know dx dt, because that's what I'm trying to find. I've got values for r and for dr dt, but I don't have any number to plug in for x right now. I need a number to plug in for x, or else I'm not going to be able to solve for dx dt. In order to get that, I'm going to go ahead and I'm going to redraw my picture, or at least my triangle. And I'm going to this time include the when information. I can't include it until I'm done with the derivative. Never use that r value until the derivative's done, or that when value in general. But now that the derivative's done, I can use it. And I can say that was 12. At this point, r is 30. And I could actually solve for a value of x right there, right? X squared plus 12 squared equals 30 squared. So x squared is going to be 756, and x will be the square root of 756. So I'll just plug that in for my x value. So let's plug everything in. Square root of 756 for x, times dx dt, which is what I'm trying to solve for, equals the r value, 30, times dr dt, which was negative 3. So dx dt is going to be negative 90 divided by the square root of 756, or about negative 3.27. And units here would again be feet per second. Notice that it turned out negative because the boat is approaching the dock, so x is getting smaller, right? All right, we will pause there and pick up a few more examples in our next video.